Hello students, this is the recording to go over the last few slides of the Unit 2 Chem project on elements. So we're going to go ahead and go over slides 11, 12, and 13. 11 and 12 are all about electronegativity, and then slide 13 is just your reflection. So let's go ahead and talk a little bit about this. Please use the definition from the recording, not Google, to explain the electronegativity trend in a period or row. So let's go ahead and take a look here. Here is our definition that we talked about in class. Right here, of the fact that in periods or rows, right, which are the ones from left to right like this, all right, we know that atoms have the same number of shells, and so as we move to the right, electronegativity actually increases. So electronegativity increases. And the reason for that, you need to have this, is that electronegativity is higher to the right because there are more protons as you go to the right to pull in that same valence shell. So for example, this is period 4, row 4, and therefore they have 4 shells. And again, if you take a look here, all right, as we go to the right, you can see that you're getting more and more protons, right? This one has 31 protons, this one has 32, right, all the way down to 35. And so as they have more protons, more positive protons, they're able to pull in the negative shells, that same number of negative shells, right, the 4 shells, and that makes them smaller. And as we learned in class, smaller atoms are more electronegative or attractive because it's easier for them to reach new electrons. So the example that we took a look at specifically in class was between carbon and nitrogen. Again, they're both in the same row. They're both in period 2, and so they both have 2 shells, which you can see down here in green. They both have 1, 2 shells, 1, 2 shells. And taking a look here, you can see that the only difference between them, right, they look very similar, but the main difference between them is that nitrogen has 7 protons, whereas carbon only has 6. So since nitrogen has 7 protons, it has a little bit more positivity in the center of its nucleus in order to pull in electrons, which are negative or the opposite charge, right? Opposites attract. And so they're able to better pull in these shells, and therefore they are smaller, and therefore more electronegative. They're, what we said in class was like cuter. It's easier for this nitrogen to reach out and get a new electron. Whereas for this carbon, the carbon has to move a little bit further. It has to attract over a longer distance to try to get a new electron. Remember that the exception here was our noble gases, which none of you should have chosen a noble gas for your project anyways, so this is kind of a moot point. But just keep in mind that noble gases, or group 18, our last group right here, made of helium, neon, argon, krypton, etc., they are an exception. They have no electronegativity just because they're in group 18. This means that they have 8 valence electrons. Which means they have full valences, and so they're completely happy and stable. They aren't going to try to attract electrons or get rid of electrons, so they're not very electronegative, they're not very non-electronegative because they don't care about electronegativity at all, so they don't count, okay? So that's going to be the definition that you need here, mainly that electronegativity is higher to the right because there are more protons to pull in the same valence shell for a period, okay? So that's what you should go ahead and put here. Feel free to copy that definition, copy definition that I provided, okay? So then it says, based on ptable.com, what is your element's size compared to the other elements in its period or row? Remember, the reason that size is important is because we said that the smaller you are, the more electronegative you are because you are more easily able to reach new electrons, right? Remember, we said that they are like cuter. Okay, so that's why the size of the atom is important. So from ptable.com, you're going to go ahead and take a look at the size of your elements. So again, click on this link right here, and you can go ahead and open up ptable.com. I'm going to go ahead and use silver. Please do not use silver because silver is not an option that you are allowed to use. All right, so do not copy. You are not allowed to use silver. All right, so let's go ahead and talk a little bit about this. So in order to look at the size of our of our atom, we can go down to where it says radius. All right, we're going to go ahead and take a look here. Instead of calculated radius, we're going to go ahead and change it to empirical radius. Calculated it just means that this is like the theoretical radius, whereas empirical is actual measured radius. So we'll go ahead and take a look at the empirical radius and then just click on the bar here. So make sure you actually click on the bar there and you can see the radiuses pop up. So the cool part about this is, first off, you have a color key, right? So if it's light blue, that means it's really tiny. If it's dark blue, that means that it is really big. And if it's somewhere in between, right, medium blue, that means that it's a medium size. You can also actually see the numbers here. So for example, you can see that cesium is one of our larger atoms here, made up to 260 radius, whereas fluorine is one of our smaller atoms here with a radius of 50. Okay. Remember, if you think about radius, radius is the distance from the center to the outside. Okay, so talking a little bit about silver, for example, I can see in two different ways that this is probably a medium-sized atom, because not only can I see that it has a number of 160, which is about halfway between 50 and 260, but also it's a medium blue, right? So I can see that it's definitely a medium blue here. And so for me, what I would go ahead and pick, all right, taking a look here, is I would pick medium for silver. Do not copy, because you're not allowed to use silver, but this is my example. Okay, so I would say it has a medium size, which probably means it's going to have a medium electronegativity. All right, so let's go ahead and then take a look here as well. Right, so taking a look as well with our electronegativity in a group or a column. So I'm going to go ahead and define that in a group or a column. So let's take a look back at our slides here. So in groups, atoms have different shells. Remember that as you go down in a group, so for example, let's take a look at group 14. All right, this is group number 14. As we go down in group 14, we're increasing their periods. So we go from period 1 to period 2, to period 3, period 4, period 5, etc., etc. So as we're going down, we're increasing the period in this group, and that means that we're also adding shells, right? So carbon has 2 shells, silicon has 3 shells, right? Shells. And germanium has 4 shells because it's in period 4. Tin has 5 shells because it's in period 5, and so on and so forth. So as we go down, we're adding shells within the group. So in groups or columns, atoms have different amount of shells, and at the top, remember at the top, that's going to be the lowest period, and therefore also the lowest number of shells. So for example, you can see here, right, that carbon has the lowest number of shells here with only 2 shells. And so since carbon only has 2 shells, that makes it a lot smaller than every other atom in its group. And so that is going to give it higher electronegativity, because smaller means cuter, smaller means it can more easily reach new electrons, right? So electronegativity is going to be higher at the top of our groups because there are less shells and they are smaller. You can see an even better example down here. This is from group number 1, the alkali metals right here. You can see that lithium, right, again is in period 2, and so lithium has 2 shells, whereas sodium right below it is in period 3 and has 3 shells. You can see it's getting bigger. And potassium in period 4 has 4 shells. And so again, lithium is going to be more electronegative because it's smaller. So smaller, more electronegative, right? Doesn't have to reach as far to get a new electron, right? So it's going to be a little bit easier for it to reach electrons. Right, so right here. Okay, so again, smaller is key here. This is the definition that you need, right? So feel free to copy that. Electronegativity is higher at the top of groups because there are less shells. All right, so again, let me go ahead and just write that here. So you can copy my definition from the recording. Okay, so then we're going to go ahead and compare the element size compared to the other elements in its group. All right, so let's go ahead and jump back over to ptable.com. So again, I have changed my radius to empirical. I have clicked on the radius bar, and I can actually see the radius here. I should have mentioned that when I was comparing the size of silver, the first time, I really should have compared it to its own row, right? So in this first example, I should have been comparing it to just its row here, with the exception of xenon, right? But it's very similar, right? Rubidium has 235, iodine has 140, right? So in its row, silver is still kind of in between, right? Still 160 is kind of in between. It's still medium. So that's fine. Sorry, I apologize. I did it diagonally. I should have done it horizontally the first time. But now when we're talking about groups here, all right, so in group 11, right? So this time I'm going to compare it to groups, right? So I have silver is 160, copper is 135, gold is 135. Now, interestingly enough, this doesn't exactly follow the rules. And again, the reason it doesn't follow the rules is because it is a transition metal. And we know already that all of our transition metals here don't really follow the rules, don't follow the rules well. All right, so let's go ahead and take a look here. But just based on comparing it, right, I can see that, interestingly enough, my silver actually has the highest radius, the largest radius within our group here. Okay, so right here, I can go ahead and jump back over here, and I could say that for my example, this would be large, right? So silver example, do not copy. But I do want to show you another example here, right? So for example, if we were taking a look at something like polonium, right? Polonium in its row, right, has a radius, I apologize. Let's go ahead and take a look here. Let's go ahead and take a look at carbon, for example, because we've talked about carbon a few times. So again, carbon is not an option that you can choose. But again, if I were to look at it in its row or period, right, carbon has a radius of about 70, whereas fluorine is 50 and lithium is 145. So again, this one would be medium for its row. But if I were to look at its column right here, carbon has a radius of 70 and lead has a radius of 180. And so carbon is actually small here for its group. Okay, so my example here, carbon would be medium for its row, which makes sense because it's in the middle of its period. Whereas, carbon is medium for its period because it's in the middle of its row. And carbon is small for its group because it's at the top of its row. All right, so it's medium for its period, which means that compared to other atoms in its period, it's probably going to have a medium electronegativity. And it's small for its group, which means that compared to other atoms, it'll probably have a high electronegativity in its group because it's smaller and easier for that carbon to reach new electrons within its group. All right, so maybe that's probably a better example. So let's go ahead and take a look here. Now we can go ahead and just summarize what we learned. So slide number 12 says, what is the overall electronegativity of your element? Is it higher, which means closer to 4.0, or lower, which means closer to 0.7? So let's go ahead and jump back over to ptable.com. And this time we're going to go ahead and jump to where we have the electronegativity. So click on the electronegativity bar. And again, you can take a look at examples here, right? So silver, for example, has an electronegativity of 1.93, and carbon has an electronegativity of 2.55, right? And so silver would actually be more towards the lower end. It's less than 2, so this would actually be lower. All right, whereas carbon is more than 2, so this one would actually be higher. Okay, so that should help you figure out what your electronegativity is. Again, if it's more yellow, that's going to be lower. Lower, so less than 2 usually, and higher, right, which means more than 2 usually. Okay. All right, and so now we can go ahead and just talk a little bit about that. So jumping over here, right, you can say, what is your electronegativity? Is it higher or lower? And then from our recording, what is our definition of electronegativity? We learned that electronegativity is an atom's ability to attract electrons, right? So please feel free to copy this definition from the recording. And based on this, what is your, based on your element's overall electronegativity, is it more likely to want to gain or lose electrons? Now this can be a little bit tricky if you're kind of in the middle here, but please remember that groups 1, 2, and 13 will all want to lose electrons. And so generally they're going to have lower electronegativity because they're less attractive to electrons. All right, whereas over here in a different color, let me grab a different color here. All right, groups 15, 16, and 17 are all going to have want to gain electrons because they all have higher electronegativity, which makes them more attractive to electrons. Okay, so again, I know it's a little bit tricky when you're trying to decide what's going on with some of these, but again, all of these actually have what we would consider to be lower electronegativities, whereas all of these ones right here would actually have higher electronegativities, right? I can change that color here. Higher electronegativities. So yeah, I should have specified that earlier, so this one will be higher, and right here, this one will be lower. All right, so that should help you out with this slide right here. So again, jumping back over here, make sure you define it based on what we defined it in class, and then say, do they want to gain or lose electrons? Something that you should already know because you've already answered that multiple times in your project. Slide number 13 is just a reflection. So what's the most interesting thing that you learned or reviewed about your element? Remember that I decay, I don't know, IDC, I don't care, nothing, etc. are not acceptable answers. Okay, so the most interesting thing that you learned or reviewed about your element, you did a bunch of research on your element and element compounds. So one of the most interesting things most of our students find is how our element is used. Okay, something that went well, and then something that you can do next time to improve on future projects. Once you're done with that, go ahead and submit it. I'll go ahead and show you how to submit this. In order to submit your project, you need to, if you're in Google Slides, you do need to download it. So go to File, Download, and download it either as a PowerPoint or a PDF. Please make sure you only choose PowerPoint or PDF. So I'll go ahead and download this to my computer. Obviously, if you already saved it as a PowerPoint, then you are all set. And then just make sure that you download it somewhere that you can remember where to find it. Okay, so then we're going to go ahead and jump over to our course page here. As always, go to your grades tab. Everything is in your grades tab. You're going to go ahead and scroll down until you see, oops, sorry, wrong one. Sorry, grades tab. Scroll down until you see the Bohr model here, and you'll see the submission folder right here. So go ahead and click on the submission folder, and that will open this up, and then you'll go ahead and click add a file and follow those instructions. So add a file, you'll grab it from your computer and click upload, and then grab it from wherever you had it. So mine was in my downloads, right? And I'll add that, and then I can go ahead and submit. So again, instructions here are to first download if using Google Slides as a PDF or PowerPoint, right? So again, File, Download, PowerPoint or PDF. And then once you go over here, you're going to go ahead and go to the Grades tab, and find the Submission folder. And once you're in the Submission folder, we'll go ahead and click Add a File, right? So add a file, and follow directions provided, and then finally, obviously, submit. All right, and you should be all set. All right, so that's all you need to do in order to submit your project. Thank you so much.